Okay, so question 4, a question on electrostatic charge and electric fields. So we've got a comb, and it says explain how rubbing the comb with a dry cloth. So we've got this idea of rubbing, so that's going to be charging by friction. And remember, I taught you there's two ways we can charge, or two main ways we can charge things. We can charge them by friction, if it's two insulators, or we can charge by induction, using a known charge to put a charge onto something else. So we're going to rub the comb, and it says the comb will become positive. So I'm going to put some positives on here. Well, the only way I can do that is I've taught you in terms of solids, I cannot move solid charges, but I can, the positive charges, but I can move these tiny little electrons. So for the comb to have been positive, the electrons, the E minus, must have gone to the paper, and these have become negative. And then I've just got to put that into words. Now, I have taught you, be really careful with saying where the electrons go from and where they go to. So first part, this is charging by friction, and I've used the idea of rubbing there. So next part then, we're going to transfer negative electrons. Now comes the from and the to, and then the other part I taught you is just talk about this net overall charge. So from the comb to the cloth, leaving a net positive charge on the comb. I mean, ultimately now, the protons are still in the comb, and we've moved some of those electrons. So if I wanted to show off, I could say there's more protons than electrons in the comb. That's that question. It says, explain how the positively charged comb picks up small pieces of paper. So this is now this idea of charging by induction. And I taught you this in terms of, imagine I've got a wall with an equal number of positives and negatives in it, and I bring a negatively charged balloon. As I bring that balloon back, I can't move positives, I can't move the protons in the middle of the nuclei, but the electrons will repel backwards, and that will then lead to the front of the wall having an induced positive charge. Now, over time, what will then happen is electrons will leak from the balloon through the wall, and then the balloon will fall down. And these electrons will move back into their positions. So that's how I taught you in terms of the charging a balloon and why it sticks to a wall. And we said that this is charging by induction. So that first question was check-in, charging by friction. This is now charging by induction. So your model answer, this is charging by induction. The positive comb attracts the electrons in the paper. So what we can imagine now is, I'll just draw a blob. There's my comb. There's my paper. We said that this is positive. What this is going to do is it's going to move. Let's imagine the electrons are equally spread. It's going to move them forwards here. So the front of the paper is going to become negative. And then those opposite charges attract. So this is charging by induction. Positive comb will attract the electrons towards the front of the paper. So to the front surface of the paper. So I've not only said it's the electrons that are being attracted, I'm saying where to. And then the positive comb then attracts the opposite induced charge in the paper. So the next part is I'm saying the comb is positive, the front of the paper is negative, and those opposite charges will attract. Oh, how annoying, I've put then, boo. On to the next bit. Which of these diagrams show the shape and direction of the electric field? So we've got point charges, and we've said, well, if I've got a point charge, that'll be equally spread, moving perpendicular to the surface. And we said, well, if I've got a positive charge, and I taught you pout and nin. So here I've got a positive charge, pout, they need to come out. So always remember negative charges, they go in. So remember your pout and your nin, and therefore that's going to be A. These here are trying to confuse electric fields with circular magnetic fields that I'll be teaching you soon. Next one, figure 7 shows two metal spheres. Sphere A is fixed to the table and B can be moved. So we've got this is able to move forwards and backwards, but this is stuck in place. It says both spheres are insulated from the table and given a negative charge. The force between the charged spheres is measured. So you can imagine if I give that a minus charge, and if I now give this a minus charge, this is going to be pushed backwards because opposite, same charges repel. But now it says explain why in terms of electric fields. Why is there a force? Well, we've just learned about pout and nin. So these are negatives. We've got these fields here. And remember, these fields go on forever. It's just the strength, the spacing of them that changes. So the overall field, it has less strength. This negative here has its, so this first one here has its electric field. This has got its electric field, but ultimately it's been placed into this field as well. So now I've got this effect here. And what's going to happen is these electric fields are going to interact, and that is a key word. So your model answer for this now: explain why in terms of electric fields, why is it that B experiences a force backwards if they're given the same charge? And it is, just say sphere A has an electric field. Sketch it on the diagram if you want, like I did. Sphere B is in that field and the two electric fields interact. So we've tried to get this idea, a bit like when we looked at magnetism last year, and we looked at this last year as well. So if I've got a positive and a negative, and remember pout and nin, so I'm going to go like that. And if I've got, say, a, what shall I do? Let's do a positive and a positive. We've got that. And because of this, because we've got an interaction between fields, there is a force. Next part, sphere B is moved and the force is measured. So I've got distance, so I'm moving that sphere, so the distance between the spheres. As I move it closer, going this way, or further away that way, I can experience the force. And we can see, well, as I increase the distance, the force goes down. And it is not directly proportional because there's no straight line. So what we can see now is, okay, I get this idea. This is a non-linear relationship. So it's now state the relationship and then say whether it's linear or non-linear. So as distance increases, force decreases. Easy. Okay, so as that increases, this decreases. And the next part is, it's a non-linear relationship. Now, if you wanted to, you didn't want that idea of non-linear relationship, or if you're asked to give more detail on this, what it's saying is moving a small amount at the start has a big effect, whereas moving that same distance here, you can see it has diminishing returns. So it's this idea that there's at smaller distances, there is a bigger effect. And that's that question done.